Okay, thanks for the introduction and for the invitation. It's always an honor to come back to USC. I think I learned a lot here. And it's also good to do these things in person again after COVID. They have a bit more meaning. This is really tricky, but we'll try.
You have to rotate it this way.
This way, okay. So just a couple of things. I mean, I think I learned really a lot here at USC. And one of the things that I learned was that you need to sort of study both breadth and depth, maybe from the provost's office, maybe from Doris, and from a collection of people. So we're going to do a deep dive here in a second, and it's going to get really technical probably and nerdy. But I want to just say that like the reason that we're doing all of this work and why we are so obsessed with materials is really deeply rooted in the fact that construction industry has huge impact in carbon emissions and environmental impact overall. And that is, I'm not going to show you like graphs about this, and we're not going to argue over like whether we should use trees or keep the forests or not. But I think in general, as architects, we have an insane now responsibility to try to tackle this problem. And I'm going to show you some examples of how we do that in my lab and with some of my partners. But I think the biggest sort of takeaway is that like this is an opportunity, but also a huge responsibility now for architects to address. And building materials and building construction are like probably the biggest area where you can operate in order to actually have an impact to address these problems. So the talk is called Building Material Intelligence. Okay. It's called Building Material Intelligence, and I'm going to walk you through a sort of conceptual background of how we get to this, and then show you 3 or 4 built projects, and a little bit about what we're doing in the lab now, like what's on the boards. So we're in an architecture faculty here. I talk in a lot of different types of faculties, but we like to preface this in this kind of architectural history lesson, which is now a bit outdated, but you might still learn it. So Louis Kahn sort of metaphorically asked the brick what it wants to be, and the brick says it wants to be an arch. And this type of kind of, let's say, addressing like how materials work in structural geometry and shapes really well is something that now a lot of engineers and architects have tried to address all around the world, but they leave out a sort of fundamental issue, which is that like you might have the best geometry, so the arch might be the best geometry for a brick in compression, but how is the brick actually going to get into the shape of an arch? And if we don't address that part of the problem as well, then it doesn't really matter, because if the effort that we need to put in to get it into the shape overcomes the savings from the shape, then we have a sort of big problem. So here you see Winston Churchill, I guess a very smart, powerful man, but he's just putting the bricks in a straight line. And I guess here at USC, you put them also in straight lines and hang them in the seismic zone. And I don't know, they do even less. But the point is that like we need to sort of think a little bit more about how we arrange materials, and not just how we arrange them, but how we get them into those arrangements. So another, again, maybe even locally relevant way to contextualize this is with Ray and Charles Eames, who said that design is simply a plan for arranging elements in such a way as to best accomplish a particular purpose. And they did this in the 40s and 50s based on a lot of work with plywood and also composites on a furniture scale, but also working with a number of different industries. So this is an airplane fuselage. And so there's really a sort of mix of functionality, but in the end, it all boils down to like how we can, or like sort of how we arrange the material in space. And the difference of what we're doing now compared to what they were doing, I guess, half a century ago, is that we now address this problem, or we approach this problem from the point of view of how we can use computation and computational fabrication in order to have a sort of entirely new ways of actually getting those materials into space. So into the right places. So this is a shoe from Flyknit. This is also now a bit dated, but it's like a really simple thread, right? So not huge like classic material science innovation. Same threads, maybe some different colors, but now we're using computational design and digital fabrication in order to come up with like entirely new functional and also aesthetic patterning within this. In architecture and building construction, even within the institutes and the places that I have worked, typically this type of synthesis between the kind of digital fabrication machines and the material tends to look like this. So it's like, what can we get from the car industry? This is a Tesla fabrication plant that's probably really close by here. I think it's in Southern California. But the problem is that then these types of processes don't really address the building materials that they work with. And we can argue that, okay, even if we apply them to these types of building materials, so this is a plant in Idaho, actually, where the robots are automating basically stick frame panel construction. So even if we have these tools, again, now they're just putting the materials together in the same way that humans would put them together. But this is a robot that can lift like 1,000 pounds probably. And then at the same time, the architecture that we get out of that is the same architecture. And that to me doesn't really make sense. And I don't think that in the end, it really means that we're utilizing what the materials can do, because these are the same materials that we've worked with for a long time. And now we have these ways of approaching them differently. So one way that we propose in my group in order to address this is to come up with this idea of material programming. And we define material programming as a method of design in which we can use computation and fabrication to encode functions and structure directly within physical material systems, of course, based on what the materials can actually do. And through these fabrication logics, we can develop new methods of lightweight and light touch construction. And we can also apply these in different types of building components and building systems. And the advantage being that because we rely on what the material can do, we can embed a lot more functionalities without going towards these sort of electronic control systems, which are good for some things and maybe not for others. But the best example of material programming actually probably still comes from nature in something like the spruce cone, which I would encourage you to go get some spruce cones from the park over there and try this out because it will work 100% of the time. So what happens in the spruce cone is that the breadths or the scales of the cone, when the cone falls from the tree, they start drying out, they lose moisture, and they open up automatically in order to release the seeds from the cone. And the way that this works is that there's no like Arduino kit or like sensors or actuators like embedded in this. That would be insane if you think about how many pine cones there are on Earth and how many breadths open. I think it would be like a billion, like billions, right? So similarly for buildings, like there's lots of electronic controls. That's really great. But like if you need a Arduino in every window that you have, you're going to start to reach a sort of financial and kind of complexity problem. So the way that it works in the pine cone is that the structure of the cells inside of the breadths give it this functionality to both protect the cone, but then also actuate through a change in moisture. So when we think about the pine cone, we can define this kind of material programming logic within here. So we have an input that's a sort of sensing the change in moisture content in the air or in the relative humidity in the air. Then there's a physical computation, and then there's an actuation, and the actuation being the opening of the scales. And we call this programming because we have a reliable sort of comparison between an input and an output. So there's no like digital signals here, but we can define an equation or a relationship that is repeatable, and in that case, we say it's a program. The really interesting thing is that wood as a material, very similar to the pine cone, is made of cellulosic materials. And it also has the same function of changing its shape when it changes its moisture content, which is what powers the movement in the pine cone. And we call this type of action hygromorphic, hygro meaning changing with water, and morphic meaning changing shape. And in science, this is also called hygroscopic properties, but this doesn't relate directly necessarily to the change in shape, so we'll say hygromorphic. And in the wood, the way that this happens is because wound in these sort of cellular structures within all types of wood, there are these little cellulose fibers, and those get bigger and smaller when they have more or less water inside of them. The other really cool thing about wood, which you might know if you've ever like done any woodworking, is that it has different anatomical directions. So you can define these as sort of like a coordinate system within the wood. And the shrinking and swelling or the hygromorphic properties, as well as the structural properties, are different within this coordinate system. And that's really useful because that means that we can actually direct the movement or the change in shape within the wood by orienting it in these directions. And that's very different from a lot of synthetic smart materials, which tend to be isotropic in nature, which means that they expand and contract in all directions equally. Which is great for some things, but not great if you want to be able to actually like steer or tune the behavior of the material. So you might know these hygromorphic properties from something like this. This is like shingles cracking in northern New England because they experience this change in moisture a lot over time, or your table cracking, or I think the example I see the most is like if I put a wooden spoon in the dishwasher, it comes out all wonky and it's not so great, but it doesn't break, which is pretty impressive. Also like your doors don't shut in the humid season and then they like have huge openings in the dry season. So this is like an action that's in all wood, and we don't like treat the wood or anything like that. It's just sort of innate to the material. It's also really well studied in timber construction and woodworking because it tends to cause problems like as you're working with the board. So if you don't dry out your timber properly and you cut it wrong, then you get all these sorts of these like large deformations that you can see on the right where you don't want them. At the same time, the forces are really, really strong. So I think one of my students once calculated with like 4 blocks of wood, they could lift their car off the ground if they if they like hydrated and dehydrated the wood properly. So it's really, really strong. You can use it to split rocks. That was done in ancient times, much stronger than any synthetic materials that I know of that have these properties. And this change in shape happens like in relatively normal conditions on Earth. So we're not talking about space architecture, really popular things to study at MIT. We're talking about things here on Earth. It's like the material is made here on Earth, and it is really also designed to function very well here on Earth. Again, like if we apply kind of like digital lens or a programming lens to that, we can take a block of wood and we can actually define scientifically from both literature and from physical testing how these different properties behave in the anatomical directions, which are defined as tangential, radial, and longitudinal. And you can see that the values are very different in the different directions. So that becomes our kind of like base for our programming. That's the sort of like inputs that we use, that we put into our like digital and physical code. And very early on, I did a lot of work as a master's student on how we can upscale these properties. So how we can take just a basic log and actually break it down logically in a way that makes sense for reshaping it through the hygromorphic properties, and then like basically putting it back together so that it actually does this. And this we call form generation. And now I'm going to explain a couple of projects that like fall into those lines of form generation. But first I have to explain a little bit about the research group where I work, because I say we, but it's not metaphorical. It's actually like really a large team of people across different disciplines that work on these types of projects. And the projects range, the sort of approach of material programming is applied across all different scales, even though the approach is very similar. So we work on things down to like wearables and furniture, as well as building facades. And then on the bottom left, like full scale load-bearing building components, but the principles are all like sort of the same, and it's kind of the same team, mostly made of architects, actually. And in Stuttgart, this is where our sort of like group sat. So we worked within an institute, the Institute for Computational Design and Construction, which is run by Professor Achim Menges, and we also worked really closely with the Institute for Building Structures and Structural Design, which is run by Professor Jan Knippers. So that's like sort of where our sort of like internal group sat. But we also work with larger funding bodies and centers. That's what you can see on the top, as well as other institutes in the university, industry partners, like ranging again from building construction to footwear, as well as many international partners. So it's like we are interdisciplinary, but also working like sort of across the range of fundamental research as well as industry-sponsored work. These are the people that are involved here. You might also know Tiffany Chen, who was a USC undergrad, BArch grad 1 year after me, who also sort of followed a similar path through Cambridge to come and work in Stuttgart. And we had a sort of like 6 or 7 people team in Stuttgart of really great people coming mostly from design backgrounds. And then now in the University of Oregon, I have a much younger team of undergrad and graduate students that are also working on these topics. So a lot of the work that I'm going to show now relates to the group in Stuttgart, and I'll give you a little hint of what we're doing in Oregon. So I'm going to run through a couple of these projects relatively quickly, but just remember that they all use this concept of material programming in some way. So the first project is the Urbach Tower. This was made in 2019 in southern Germany, and it's still there. And a bit of background about how this project came to work. It came to be after my master's thesis in Stuttgart, we were looking for, and we successfully got funding from the Swiss Foundation, which funds industry innovation in Switzerland, to think about how we can upscale these hygromorphic self-shaping concepts to work really on a building scale. And at the same time, like mass timber is really big now in the US, but it's been around for a long time in Europe. And still, like the sort of like impact of mass timber is in these really like kind of boxy forms, which also in many ways also in engineering are kind of like grouped into this category of like still, it's like we have now mass timber, but we're still like kind of applying it as if it was like precast concrete panels. And you see that in the architecture that results from it, right? So it's this very boxy result, which is great. It's like a good like first step. But what we want to look at is like, what would the sort of architecture that really belongs to timber or really emerges from timber and these digital technologies look like? So it's not going to be like classic, I don't know, timber frames. It's also not going to be something that's like emulating another material system. It's going to be something different. At the same time, CLT or cross-laminated timber that you see here, it actually has a material programming logic to it with the layers and the layups that exist. It's just that this has always been geared towards structural performance. So taking that logic, we also looked at, again, from the architecture background, so this is from Gigi Shirley's book, and I use this in every talk. So, okay, we can make flat panels, and then we can just make them thicker. That's the classic engineering approach, right? So doesn't span, can't take the bending, let's make it thicker until but this is like the cat chasing the tail, right? Because as we get thicker, then get more material, then it gets heavier. There's also this approach, a very simple approach. You can use curvature, you can use geometry. So you do that, and then you can span a much larger distance with considerably less material. In wood, you can make curve shapes. It's just way more expensive. So you see this in a lot of like really expensive buildings for like Swatch, for example, or Omega. Those are like Swiss watch companies. Or in golf courses and things like that. So you can do it with beams, but it's very expensive and exponentially more expensive as you sort of become more complex in your curvature. And the processes of how to like get it there are relatively crude. You have to sort of bend it, or in most cases, you just build a big rectangle and you cut out a curve shape. That tends to be cheaper, sort of in practice. And what we proposed, working with industry partner Blumer Lehmann in Gosau, Switzerland, is that we could implement this self-shaping sort of approach of generating curvature through the hygromorphic properties into their existing workflow of sort of drying the timber from the trees. And then we could curve elements in a sort of parallel process and then glue them all together in order to get a bigger curved element. At the same time, we work really closely with wood scientists and engineers in order to develop methods for predicting this type of movement. So we work with really like analytical equations like this. They're from the 1920s that work really, really well. They were developed for bimetals in optics. I'm sure that Doris knows these equations very well. they're awesome. They work really, really well. But we also work on really high-tech ways of doing that, which in which there's modeling methods that numeric modeling methods that are being developed to model hygromorphic properties in wood. And there's a lot of funding in this because if you imagine that like you have a 50-story building and each story, like even if it just moves like a few millimeters, by the time you get to the top, you've got a really, really big problem. And someone actually Thomas Robinson from Lever told me a few weeks ago in his lecture, he said that in a normal stick frame building, you get like maybe 5 inches off by the time you get to the top of the building, and this is really a problem. So it's a problem that we have to address, and we just use that, we like piggyback onto that modeling here for a kind of like extreme case. At the same time, we work as architects, so we were asked to design a tower structure. That might seem kind of random, but it's perfect because it gives us a sort of opportunity to show how strong this can be and also how light it can be. So working with Grasshopper and Rhino and also some like connections to engineering software, we're able to come up with these geometries that work really well with the types of shapes or surfaces that we can generate using the self-shaping process. This is a really simple, looks like a really simple Grasshopper exercise, if any of you know that. I would challenge you, if you think you can recreate it, go for it. There are a lot of YouTube videos of people that have done it incorrectly. But here it's about really matching sort of what you can create with the research to come up with new forms. These forms are particularly interesting because they are sort of like segmented shells, so they're not continuous. And they're made from single curvature elements. That's what you can see here. So it's not like a dome or a hyper shape. But when we put all of those elements together, we do get a hyper shaped sort of double curved overall geometry, which works really well structurally. So we end up with a kind of corrugated surface structure that doesn't fit into any categories or typologies, but works really well structurally and also aesthetically. And then we model a lot of the connections, of course. That's where the digital planning comes in and really, really works. We'll try to pick up speed so we can go through more of these. So the process then here, it's like very digital. We do tons and tons of planning, but then the manufacturing starts here with this guy and explaining to him in Swiss German, which is a totally different language that changes constantly, how to actually sort out the boards as they go through the line. So this is the code or the programming code that came from all this work. And it tells him simply which boards to choose out from this sort of continuous throughput of boards. And we're just choosing on moisture content and grain angle. So there's nothing that complicated. There's no special wood. It's not the more expensive wood. It's just like telling him to sort out based on simple parameters. And then we glue those into flat plates. Then they go into the kiln where they will get dried mechanically. And this is what happens inside the kiln. So we have these huge flat plates. And kind of magically, as they lose moisture content, the curvature emerges, sort of for free. They do this on a sort of massive scale in the factory. So it's a parallel production process, which is different from using a mold, which is really great. So they all shape at the same time when they put them in the kiln. You don't have to wait. And then here you can see already, even though they look really shallowly curved here because they're so long, you can see how that gives stiffness to the panel. So this is a like 1 inch thick panel, and it doesn't bend in the opposite direction when we pick it up with the crane. So then we put all of these plates, we sort of glue these together and we lock them into shape, and then we build them into bigger components. We have to structurally test this to prove that it works as normal CLT would in a sort of structural situation. And then we use a machine to sort of carve out the detailing that provides the connections and also the interface to the ground. So this is like, these are, I mean, I have to work a bit here with the math of the units, but these are like 14 meters long, about 35, 40 feet long. And then we have this machine that comes in and it's basically just like trimming the edges, and it's going in with a 4 millimeter drill bit like a dentist and pre-drilling all of the holes for every screw. that will be used. So then on the then they get pre-assembled into these packets, also with a timber facade. And then on the site, all the holes are there for all of the screws in the connections that have to happen on site. That means that they can, it's like 100% prefabricated. They come in here and like 4 guys put the whole tower up in 8 hours. And that's sort of especially important because this was in a sort of natural preserve site. So the site impact is really sort of limited. In contrast, it took 2.5 weeks for the concrete fabricators to put in the foundation. So 2.5 weeks and 8 hours on site. It's a really big difference. And what we get is this sort of structure that from the outside has these really sharp curves, but on the inside takes on a sort of slightly different type of texture that I'll show in a minute. And it's 14 meters tall, like it's basically acting like a cantilever. It has to take wind load. But at the same time, it's only 90 millimeters thick. That's like about this thick. And if Sigrid was here, we could debate how to compare that to an eggshell. And that would be really fun. We have different opinions about that, but I think it's thinner than an eggshell, proportionally to an eggshell. But maybe more interesting is that architecturally on the inside, we get this incredibly soft, almost like pillow-like texture, which isn't common from timber. So it's like, now we have curved surfaces in timber, this is what we get. But it's doing a lot of work. So this becomes a kind of like chapel. It doesn't have like a huge functionality. It's kind of like the little chapel here at USC, if you've ever been there. Or some of these Zumthor projects that sort of sit in the landscape and change your interpretation of the landscape around you, which is a very known situation, puts you in a very unknown situation. At the same time, what's most impressive is that here the timber is doing all of the work. So it is a monocoque shell, it is the cladding, it is also unfinished, like safe for this child to touch, right? So we don't need to treat it with anything special on the inside. And not only that, but it also is like the machine that shaped itself, right? So it's like becomes actually the fabrication machine and the structure at the end. In order to like prove this to the local building authorities, we have to monitor it. So we don't, in this case, we don't want it to change shape afterwards. So we monitor the moisture content in the wood, and the moisture content will still go up and down, but the geometry doesn't change. That's what you see on the right. So like super normal levels of change that happened most at the beginning, probably due to settlement in the facade. And then it sits in this landscape really beautifully, and it's also become a kind of like local landmark that's accessible primarily by bike and by foot. And we're hoping that it will stay there for many years to come. At the same time, on the research side, we continue working on it. So these are some leftover pieces from the project that we turned into structural components as like demonstrators. And we're working on how to apply this as wall and roof components. We're also at the moment constructing another taller tower. So this one will be 22 meters tall in the end. And this has this sort of staircase in the middle that allows you to actually experience like up through this sort of winding form. And again, I'll go back here, but what is like fantastic about this is it also represents a huge shift in the perception of the materials that we use. So here the timber is taking all the wind load, right, as a sort of shell, and it's taking the sort of gravity load and of the platform, and the steel is really just like kind of there as a staircase. And this is like an inversion of how we would typically do this. So usually the steel is used to reinforce the timber, right, and provide all of the strength. And here, because we get the geometry of the timber right, hopefully, the timber is doing all of the work. And that's huge because that represents like a total shift in what we think about what materials can do, right? We could probably get rid of the steel even, I would suspect, if we wanted to have a sort of more solid staircase. And also impressive is how thin it is. So we don't need to use a lot of timber in order to do that, as long as we get it into the right shape. And this is really impressively, was released today actually, that now this has been fully assembled on site. So you can see it here, you see the huge components. These are 80 feet long on the truck coming in pre-assembled and then getting lifted up into the final geometry. And you see also the Swiss and Austrian Alps in the background. It's a really beautiful site, and so if you go there after April 26th, you can climb up there and see how it looks. At the same time, we're also working on another project which uses these in structural walls, almost like shear walls. Again, where we can make them thinner, and we also get a really nice architectural experience. But maybe even more interesting than that is that through this, we also start to develop more machine learning based methods that utilize machine learning and machine vision in order to take a different approach to how to predict the geometry and the shape change. So through these new projects, we record tons of data in the manufacturing process, and then we mix that data in a kind of hybrid method with synthetic data that comes from the models. And we've proven that, like, through all of that, we can actually outperform statistically the Timoshenko model, which is the analytical model, as well as these sort of ultra advanced models that use typical numerical methods. Okay, now I'm going to show you, I think we'll only have time for one other project probably, but I'll show you this one. So this is, so from there we can also apply these principles to form adaptation. So here, not necessarily like just generating the form, but letting it be in a way, designed in a way that it can actually adapt to changes in the environment that happen. We'll show this through a project which is called the LiveMats biomimetic shell. It's also in southern Germany, and it's actually constructed now. And this built on a lot of work previously in the institute that looked at how we could use wood materials and new materials in a way that they actually adapt and change their shape in relation to the environment. The concept is really similar because we use wood-based composites. The difference here is that we need to reconstruct the material, like we're working on smaller scale, and like timber, it has an existing structure. So instead of utilizing that existing structure here, we take it apart and we put it back together into new types of materials that where we can like further tune how they work. And we do that on 3 different levels. So one is really in the materials themselves. So working with plastics engineers, we actually take cellulose fibers, which are incredibly cheap. It's like the cheapest material on earth, I've come to start to think, that's used actually as food additives, and we mix that into bioplastics. So that's on one level, we can tune them. And then on the next level, we use a 3D printer to sort of structure them up. So this is on the sort of millimeter scale. And then we use our more architectural and design scale, typical scale like approaches on this sort of multi-millimeter level in order to design motion mechanisms. And this is what we get. So this is in a lab test here, so you can see it opening when we have a high moisture content. This one is sped up. And then when we lower the moisture content in the lab down to 30%, which is you still experience on Earth, it closes up. And then this is the best part of the whole video. So here, our mechanical system actually in the chamber malfunctions. So you can see it's like flickering, right? And you can see how quickly the materials respond, right? So they're like hard-coded to the changes in moisture in the air on a really direct level. And the way we make them is from this sort of powder material. We integrate it in, then we 3D print it again with like the basic off-the-shelf, the cheapest 3D printer you can buy, but we program it ourselves. So we give also the 3D printer slightly more intelligent methods. And then we can tune the shape and the directionality just through this sort of line structure that we build up. We can also choreograph the speed, which is really, really fun. So here we have same thickness, and one operates in minutes and one operates on the far end in days, which is really, really cool. So we can do that like without drastically changing the mechanical properties, which is quite useful. And then we look at how we can apply this in a building facade. So shading in the summer, so sort of shielding from the heat, and then letting the facade open up so that we can gain or gather heat in the winter. And we work also on this one with Thomas Auer at Transolar in order to really like start to quantify this. We're not like quite there, but you can see, so this is our sort of building. We have some comfort days that are too cold. That tended to be the driving factor. Then we have some that are too warm. In that climate, that was not the biggest issue. So what we do is we orient the facade here to the south so that we can get as much in the winter or as much heat in the winter as we can. But then that means that we need to have this adaptive shading system to reliably shade that in the summer. We have the advantage here that we design the building at the same time, so we can do things like adjust the overhangs to work with our system. And then we're able to develop a sort of method in which we actually build this kind of like almost like a framework, right, for testing these materials. And the idea is that our materials will go into the facade now, and then in a couple of years, that it's built so that other people can test materials in there as well. So our lab designed this whole framework, like down to the detailing. We did it requires a ton of material tests. These things can be sometimes unpredictable. And we have to take into consideration like UV exposure, for example. This is the video that I really wanted to show you, Doris. So this is a lab test. So we have this going. We did this over COVID. It was great. We just like stick it in there, let it go for like a week. But what you should see here is that like, okay, beautiful movement, right? In our system, really great. And then at some point in here, you will see that before our system fails, the lights actually start falling off, if I have the right video. And the sort of like testing system itself like actually starts to fail before our sort of material system. Maybe I got the new edited video, so you want that video. Okay, but what you can see is that we have like an insanely sort of coordinated and reliable movement, which is not, it's like very natural, but it's not something that you would ever expect with a machine. I've never seen a machine that can move like that. Doris, some of your work gets to that, right? But you still have like always like a popping, right? Or like a flip through. Right? So this is completely silent, 100% silent, I guarantee you. Okay, so that's like how that works. We installed it then live, so we tested it in our lab for like over a year in a facade that was built up on a scaffolding at the exact orientation and height as it would be in the building in order to prove it. A lot of it failed. We had to like redo this over and over again. And then we installed it in the building, 12 square meters of this, and we could print it with a sort of farm of 12 printers in like around a week probably. And again, we used like so little material here. So the material cost here is so low because the cellulose powder that we buy, which is doing all of the work, like you buy it normally by the ton. So we had to pay extra money in order to get like a sort of grain bag full of this cellulose powder that we use here. And that does all of the work, right? And it's the technique that we apply to that relatively like dirt cheap material that gives it the intelligence. This building was also featured recently on the cover of Interior Design. And you can see there the sort of facade system from the inside. And we're currently like monitoring that now over a relatively long period of time. We've also, I'll go through these really quickly so that you can see them, but I'll just click through. So we also have applied this on a furniture scale. So taking similar principles to material programming and how we can use wood. The idea here that you actually can do form generation in situ. So we have the wood sort of 2 or 3 layer systems here, and then inside your house, this happens overnight. And then you have a finished piece of seating. And we're pursuing this currently with a couple of furniture manufacturers in Germany as a sort of like new technology that we can apply in furniture industry. We have a couple different versions of this. They use different mechanisms. These are not really so bio-inspired, but more mechanics inspired. So one unfurls, one sort of slips under the other and then clicks. That's the lounge chair. And this is our company that is focusing on that and also on industrializing the self-shaping technology for big components. And then lastly, I want to show you this more recent project, which is called the Hydro Shelf, which was a student project. So this was run in a design studio over a year with MS students. And this sort of puts, although it's a smaller project, it puts all of these ideas together. and is a really sort of like new way that we look at it. So this one came, like, if we think about, again, how do we get the material into these shapes? Usually, like, you would do that if you did concrete, you do it with a wood formwork. And in the end, you probably don't see that many concrete shells like this because it's really complicated to make the formwork. In Stuttgart, there's a really famous train station building that's been going up that was designed by Frei Otto, and also Werner Sobeck doing the engineering. It's insanely beautiful now. It's almost finished, but it's crazy because they actually build this geometry 3 times. So they build it out of CLT. That's what you see on the sides, right? And all that CLT is in the trash now because they have to coat it with something to get it off of the concrete. Then they build it out of steel. So you have this like insanely complicated rebar structure in the middle of there, right? And then they pour the concrete in. So it's like 3 times the work in order to get the geometry. And students really understand this. I mean, like, if you have to do something 3 times and you could just do it intelligently once, that would probably help you a lot in your studio projects. And at the same time, like, if we do shape on site, like, we have a lot of insane processes that go into getting these geometries. So this is a UN studio building. It's like in an urban context, like, it's a huge impact, right? It's also really noisy. I think we should have sound on this video to get the point across. And like, again, we're going to use the same technology. Here we're going back to the Timoshenko equation because we don't have the software licenses to use the numeric models. So we're going back to the Timoshenko equation, and then we're thinking about how can we make this not just like a curved element, but actually a curved system. So how can we actually put not just the curvature in the factory, but while it's still flat, put in the waterproofing, the cladding, and like anything else that we need so that we can essentially flat pack a building component. So the students are also working with the tutors, and there's a sort of teaching team on this, it's not just me. We came up with this system that we call the package system, where we sort of put 2 wings together that are flat, and we put all the cladding on, and then they shape on the site when we let them dry out. And I'll just run through this like really quickly. So we also work really closely with industry. That's one thing that I want to say. Like, we developed like really great algorithms with this project in order to figure out how to arrange the material for the shaping and for structural efficiency. Those don't mean shit unless we actually go and talk to this guy who runs the sawmill, which is 30 kilometers outside of Stuttgart, which we also found that one of the biggest carbon impacts is the transportation of the materials. So like, we get it locally, and that works better. And then we have to adjust our methods in order to try to like hone in how close we can get to the actual material like properties as we go. So in the very beginning, we use literature values. Then we're talking with these people, we're getting more information about it. Then when the material comes into our factory or production hall, then we can get very specific, board-specific information. That's what you see on the left. And then with our digital tools, we can actually update the design to match that material that comes in. So we're doing a bit of resource management, as well as like geometry adaptation, as well as optimization. And then we build these out again in the flat state. So these here, we have a very simple system. We had all the boards, we were measuring them every day, 2 parameters every day, and then we sort of rearrange them live. So that looks like we don't have a sorting system. So we have students basically yelling out which board should go in from their computer. We flat pack them, and then this is what happens on the site over 2 days. So these huge components, they shape out. No one is there. I can tell you 100% no one was there because we were so tired that we took 2 or 3 days off.
And so you change the humidity in the room?
We don't change the humidity in the room. So this is we did it inside as a sort of control, but the environment in the room is in control. So the doors are opening. So what we do is that we're able to actually like prep the material in a certain way with higher moisture content. But the key here is that there are 2 things, is that we actually do that without drying the timber. And if you know that like the drying of the timber, this contradicts the previous part of my lecture, but like the drying of the timber is 70% of the embedded energy timber manufacturing. So here we're able to like generate the shape and also eliminate 70% of the embedded energy in the manufacturing process and get the material very locally. So it's like a sort of hyper example of how working with the material leads like inherently to better efficiency. And we're doing a life cycle analysis on this, but I think that's not really the point, because what we see is that like it wasn't that we targeted really little things, we inherently attacked the bigger problem here, right? By looking specifically at the material. And we do a lot of science behind this. We publish, that's like the currency. And you can read a lot of our papers if you want more detail on it. But the sort of like result is that we also get a new type of architecture, right? So no structural engineer can also either really like categorize this into one thing or another. Some like that, some don't. So here we're spanning like 10 meters, and the really impressive thing, and I have to talk about the details, so we get to the detail here, again, all made out of wood except for the weatherproofing layer, which we're working on that at OSU. So cladding, also shingles that came locally in southern Germany. And then structurally here we have 24 millimeters, that's less than an inch. And it's like less than what you would use in like a sheer panel of plywood, right? It's like furniture level in terms of plywood thickness. And yet because we get it into the right geometry, we're able to use it structurally and also as the enclosure. And it's not that complicated in the end. I guess we would probably have some fire issues, right? But it's really proof that like it's not the material, we don't need super high-end material technology. This is just normal material. We get it from a sawmill like down the road, right? And when we apply our computational techniques, then we can get really amazing things out of that. We also, of course, involve students in these projects, and they have a lot of fun. They work really intensively on these, and also contribute very highly to the sort of scientific development as well as the architectural design. And I think we can just end there with the video. Is that good?
Great, thank you.
So while we watch the video, if you have any questions. Are there any questions?
Is it a quick one?
Yeah.
Okay, quick.
No, my question was about how you control the degree of the curve when it's in the kiln. Like, is there a way to basically model, like, how do you get it very precise?
So we do it all ahead of time. So we plan, like the amount of curvature is based on these parameters that we showed. So it's like how much moisture the wood starts with, how thick the wood is proportionally between the layers, and also what species it is. So it's like all pre-planned. So once it goes in the kiln, like no one touches it. That's also maybe the really clever thing, because like you and I don't know, we can like bend a piece of wood, right? A small piece of wood, but like I don't think you can bend a 30-foot panel, right? I can't. And I would need a pretty big machine in order to do that. So it's like that's almost where it becomes like magic, because like with one change in like slight change in the parameter, I can have the wood curve differently, right?
I hope you all enjoyed the lecture and thank you for coming.